recap to what we covered last week. But basically, we can just classify or we can describe a given dielectric material by 1 plus chi. This is induced polarization. So we can coin certain dielectric material by the simple constant, the relative permittivity, or we can just multiply this relative permittivity by epsilon 0, which is the vacuum permittivity, and we just call it the absolute permittivity, epsilon. And I personally recommended for you to memorize this relation between the flux density and the E field intensity is the flux density remains the same throughout the space. And if you have certain material, then locally the field intensity will be reduced by a factor of epsilon. So before we move on to new materials, let me try to elaborate this equation in more details. So let's come to the blackboard. So in space, I have lots of free charges. I have positive charges. I have negative charges. Right? So these are the free charges. The associated field will be therefore D. Okay? So I can draw a lot of field lines. Ideally, this should be straight lines. Forgive me if these are not really straight. Okay? So this is in free space. I have lots of free charges. So in this case, in free space, I can write my E external. This is like my externally applied field. And this is D divided by the vacuum permittivity. Okay? But somehow, I can insert certain material. Right? Suppose I have a slab of glass with certain thickness. In this case, I ask myself, within this material with epsilon, absolute permittivity, I ask myself, how many field lines do I have that are due to the free charges? The number remains to be 6, unchanged, right? The field lines due to the free charges, my externally applied field, remains the same. But what is reduced is, due to the induced dipoles, I might have, well, say, 3 pairs of induced dipoles. And each one of them are producing some counteracting field lines. And therefore, some of the field lines due to the free charges are being cancelled. Thus, my E field intensity within this material is weakened by a factor of epsilon. Right? So the major difference between D and E is D is related to the free charges. So basically, even though you are within such a material, dielectric material, where your field is weakened, but the field lines due to the free charges remains the same. It's only you have produced, oops, negative sign, positive sign, right? You have induced certain pairs of electric dipoles that itself generates a counteracting E field lines to make the material having weaker electric intensity. Okay? So now let's take a good look at one example. This is something very similar to what we covered for metal. Well, if you still remember, when we analyzed metal, we had a thin shell, right, of metal, but now we just replace the material, the same shell, the same geometry. You have a positive charge at the center, and you have a shell, but now the shell is made of dielectrics. Okay? So this dielectric is having a relative permittivity of epsilon r. Still, the inner radius is Ri, the outer radius is Ro. So this is, again, a three-dimensional spherical shell. Okay? So now we want to analyze what are the resulting electric field intensity. Okay? We're still dividing the analysis regions into three. When we are outside of the shell, when we're within, standing inside the material, and really inside of the shell. Okay? Still the same three regions. And we're still applying Gauss's law. Well, when we're really outside the shell, the E field intensity multiplied by the enclosed spherical surface, 4 pi r squared, is Q divided by epsilon 0. When we're standing outside, right, we don't have relative permittivity, so we use epsilon 0. And the amount of charge being included is just Q. Right? So this is nothing new. The problem arises when we are standing inside the shell. Okay? Now, in this case, when we're inside the shell, you might be wondering, well, how many charges are being enclosed? But the benefit of defining a dielectric material using epsilon, the benefit is you don't really have to care about the induced dipole charges. All you have to do is include the relative permittivity. Okay? So for a Gaussian surface with the radius r, r is greater than ri but smaller than ro, the spherical surface is still 4 pi r squared, but now you retain the charge because eventually you are still enclosing this free charge of Q, but all the effects of the induced dipoles provide some counteracting charge densities as well. So initially you might be thinking, oh, this Q has to be subtracted by some other amount of induced charge. But that's not really necessary. All you have to do is you include this relative permittivity of that given material. And that weakens your E field intensity inside the shell. Okay? So in this case, when we are inside the dielectric shell, the E field intensity, the strength, is weakened by a factor of epsilon r. And this is due to the existence of the induced electric dipoles. Okay? So therefore, starting from this point and onwards, when you meet a given dielectric material, all you have to do is include its corresponding permittivity. And you can truthfully derive its E field intensity. Okay? Now, as we walk closer into the inner radius of the shell, again, you recover the very similar result. Okay? Here, again, you are in vacuum, so you don't need to include epsilon r. For vacuum, epsilon r is 1. Okay? What does this mean? If you plot all these results of E field intensity, E, you will see two abrupt jumps. When you're outside, you have a very smooth 1/r squared dependence, right? So as you move closer to the shell, you have an increasing E field intensity. But once you reach the boundary, the outer boundary, and you step across it, you have an abrupt jump. Okay? And this is exactly the effect of the induced dipose, right? So when you are outside, you have a very smooth, varying E field intensity. At the boundary is continuous, right? But then you have abrupt jump. But once you're inside, you have again a smooth variation. But when you reach the inner radius, where you have the dielectric vacuum interface, that's where your dipole ends, right? Inside the vacuum, you have no longer any capability to form induced dipoles. And therefore, at this inner radius, you have accumulated some kind of induced polarization surface charge density. Okay? So once you step across it, your E field strength is immediately increased. So whenever you have interfaces, like one interface here, second interface here, you should always expect to have abrupt jumps in the E field intensities. Okay? One jump and two jumps. But now you ask yourselves, this is plotting E, right? This dashed line is ER. Okay? What about the D field? The D field, the flux intensity, flux density, is only associated with the free charges. Okay? It does not feel the presence of the induced dipoles. Right? So if we plot out D, it's continuous and smooth throughout. Just like the case I drew on the blackboard. For D, when even you have the interface, you have material difference, it's not changing. D is a smooth, varying function. It does not care for the induced dipoles. So in a simple case, we don't have any spatial dependence. If we have infinite charges, we have a constant field, right? And therefore the D is not a function of space. But what I'm trying to tell you is D is a smooth varying function. So in this case, we have a single charge. It is setting up some kind of field or density pattern, which is decaying, well, as a function of the distance. But for E, you can have abrupt jumps, but D remains smooth throughout. Okay? So that's a major difference between D, the flux density, and E, the field intensity. So E can have dramatic changes, but D cannot. Right? The reason is, even though you're standing inside this shell, when you evaluate D, you're only asking, well, how many free charges do I have? The answer is, I still have one. It's the same. But when you're standing inside and you ask, how strong is my E field? E field is asking, how much of the net charge do I have? Right? The net charge means I have the free charge, I have the induced charge densities. So when they add, you actually have a reduced value. Okay. Right, so basically, mathematically, D equals epsilon E. Therefore, D is really not material dependent. Right? So now looking at the math, you should be satisfied because Q divided by 4 pi r squared is not material dependent. Right? So throughout the space, it should be very smooth. On the other hand, E, once you have epsilon 0, and now in the back of your head, you should be very alerted. When you have a dielectric material, you have to multiply by epsilon r. Okay, so E is material dependent, D is not. Right? So for this case, you can also calculate, well, how strong is the induced polarization factor. You have a sudden drop in the E field intensity. It means you must have induced polarization factor. Okay? So the induced polarization factor looks like that. Why? Because by definition, the polarization factor is the difference between D and epsilon 0 E. Okay? So in this case, within the dielectric shell, you have induced a polarization factor in the direction of the radius with that amplitude. But it is also a function of space. It is a function of the radius. Okay? So the only difference between a dielectric shell as compared to the previous case, a metallic shell, is you have this polarization factor. And you have a non-zero E field intensity. If you have a metal, you have zero field inside the metallic shell. Right? So that's a major difference. Okay. So now I want to talk about boundary conditions. This is probably the part most confusing to a lot of students. So whenever we talk about boundary conditions, the problem we are trying to solve is we might have multiple or various different materials. Right? So in this case, I have vacuum, I have a piece of maybe glass, then I form an interface. Okay? I form one interface. I have material number 1. Okay? And I have material number 2. And I can have even a third material. Look at your cell phone. Right? The light is coming out of your cell phone, but your cell phone is covered by a piece of glass and some anti-reflection coating, and then you always have this protective plastic tape or something, right? So this might be your glass, reflection coating, and your piece of protective coating, or your whatever you call it, the thing you stick onto your cell phone, right? Now the question is, well, if I have some field, right, making an angle to the first interface, do we have the capability to know what is the outcoming field? Well, this is epsilon 4, right? And this angle. Well, this happens every day. even for light, think of light as the E field. Well, light penetrates through a lot of medium and reaches to our eyes, right? But do we have the ability to calculate it? For this very practical problem, we need to understand about boundary conditions, okay?